So the last thing we did in the previous lecture was to talk about this upper triangularizability. So we had the following theorem. We said any linear operator V is a finite dimensional product space is upper triangularizable via an orthonormal basis, okay, which means you can find an orthonormal basis with respect to which the matrix is upper triangular, right. So, this is the last thing we did, and the equivalent statement was really the following, that you can find a flag. So, saying something is upper triangularizable, I mean orthonormal basis is not a big deal. So, saying it is upper triangularizable is just the same as saying you can find a flag of subspaces which is a complete flag. So, W1 is of degree is of dimension 1, W2 is of dimension 2 and so on, such that each of these subspaces is T invariant. So, you have a T invariant complete flag of subspaces, that is the same as upper triangularizability, right. And we saw how, why this is true, because all you have to do is just start with an orthonormal basis of W1, extend it to an orthonormal basis of W2, extend further to W3 and so on and so forth, and when you do that, the final basis you get, you write the matrix of T with respect to that basis, it will automatically be upper triangular, right, because of this property that when T acts on some Wi, the answer has to be again in Wi. Okay. Now, this is in general without any assumptions on T, but if T is self adjoint, so that is the very important case. So, we can then do better, that is the diagonalizability theorem. If in addition T from V to V is self adjoint, in other words, so in the case of matrices, this is what you would call a Hermitian matrix. So, the operator is self adjoint, so same assumption, V is a finite dimensional product space. Then there in fact exists an orthonormal basis of eigenvectors, orthonormal basis B of eigenvectors of T. Okay, there is an orthonormal that's probably not how I should say it. There is an orthonormal basis of V, every vector of which is an eigenvector, so comprising eigenvectors. Okay, in particular, this means if you write the matrix of T with respect to B, then it will be better than upper triangular, it will in fact be a diagonal matrix. Okay.
Here also field is complex.
Complex, yes, yeah, I am going to take field complex everywhere. So, let us prove this. So, this again field is complex, field is complex. So, for the reals you will need a slightly different proof, because we are going to use the fact, as we did in the previous case, that if I have a polynomial with over the complex numbers, it always has a root. In other words, any operator on a complex vector space is guaranteed to have an eigenvalue, and that is the crux of that. Okay, so the proof is very quick, let us do this. So, we sort of need to construct a basis which has all eigenvectors, right. So, we will start with one eigenvalue. So, let lambda be an eigenvalue, we know for sure there exists some eigenvalue, let me call it lambda 1, eigenvalue of T, and let us take the corresponding eigenspace. So, let me call this V lambda 1, just be the set of all vectors such that T V equals lambda 1 V, right. So, this is the lambda 1 eigenspace. Lambda 1 eigenspace of T. Okay. Now, first question, is this eigenspace T invariant? If I add T on it, will I get back a vector in this? Yes, why? T just acts as a scalar multiplication by lambda 1, right. It is obviously T invariant. In fact, T when it acts on the eigenspace just acts as scalar multiplication by lambda 1 on V lambda. So, in particular T maps V lambda 1 to itself, and so then we use this lemma, the most useful lemma regarding adjoints, which is that from last time, recall, if T leaves a subspace invariant, T star leaves the perp invariant. Okay. So, that was what we proved last time. So, now here we have manufactured a subspace which is V lambda 1, which is invariant under T, therefore, its perp is invariant under T star. But T star equals T, that is where the thing comes in, right. For a general operator, this is all you can say, but we have assumed that T star is equal to T, and therefore, we conclude that T leaves the perp invariant. Okay. So, what we have managed to do is we had V, here is a T invariant subspace V lambda 1, and we look at its perp, that fellow is also T invariant, this guy is T invariant, so is the perp. Now, I claim that is the end of the proof, or at least it tells us what to do. So, now what should we do next? Okay. So, what you do is you now just replace V. So, it is sort of by induction if you wish, you replace V by forget V, make your vector space into this strictly smaller vector space. So, this is now smaller, remember, V lambda 1 perp has to be strictly smaller than dimension V, and instead of my operator T on it, I will just restrict T to V lambda 1 perp. I know it leaves it invariant, so it is a well defined operator. Okay. So, I replace my vector space by a smaller vector space, my operator by a different operator. Question is this operator still self adjoint? So, claim is that the restriction of T to V1 perp is still self adjoint.
T star will be invariant under, meaning V lambda 1 will be invariant under T star, so it has to be.
Okay, wonderful. So, observe that see the star is it's that unique operator which satisfies the inner product equation, right. So, what is the star? You can think of it like that, it is that unique fellow which satisfies this equation, right. Now, just take the usual T star itself. So, why is this equal to this? I mean, so okay, let us just say one easy way is let us actually check, that is maybe the trivialist thing to say. So, I claim that if you put in this particular case, I know that T star is equal to T, right. I am given that T star is equal to T. So, this is given to me, this is true for all vectors x and y in the ambient space V, right. Now, all I am doing is I am just restricting everything to the smaller space, and my vectors will all only come from the smaller space now, right. I have to check now whether T x comma y is the same as x comma T y for all x and y coming from the smaller space. So, because this is true for all x y in the larger space, it of course implies that this is also true for all x and y in the smaller space, which implies also holds for all x y in the smaller space. Okay. But that just means that when you imagine everything happening in the smaller space, this operator T satisfies the inner product equation that T star is supposed to satisfy, right. And so, by uniqueness there can only be one operator which satisfies that inner product equation, and you found one candidate which is T itself. Okay. So, it is sort of a trivial or very simple thing that if it leaves a subspace invariant, then T star is, and if the original guy is self adjoint, the restriction it is the same operator. Okay. So, now what are we doing? All we have to do now is just continue this process, that is all. So, now we have new vector space V lambda 1 perp. So, forget about V lambda 1. On this space I have this operator, that operator will have some eigenvalue again, right. So, I continue this process, look at V lambda 1 perp, this is my new vector space, in this I have some eigenvalue for sure, right. So, let me call that eigenvalue as lambda 2 and I take that eigenspace V lambda 2, okay, it is an eigenspace inside V lambda 1 perp if you wish, and by the same reasoning its perp will be invariant under T, right, and so on. So, this eigenspace and then there is an additional perp and so on. So, let me not write out the formal argument, you could do it by induction. So, you could say let me prove it by induction on the dimension of V for example, okay. But as you can see all we are really saying in this argument is you keep repeating this, okay. So, at every stage you keep repeating, you will show that you get V lambda 1 eigenspace lambda 2 etc. And of course, this process has to stop at some place because right the total dimension is finite, I can't keep doing this forever, at some point I must exhaust my whole space. So, that is the proof. So, we have finally managed to write V as in fact an orthogonal direct sum. So, you see this next step everybody there is perpendicular to everybody in V lambda 1, right. So, this first eigenspace V lambda 1 is perpendicular to all the subsequent eigenspaces because that is what that is your V lambda 1 perp, and then V lambda 2 is perpendicular to everybody who comes afterwards and so on. So, I have essentially proved that the eigenspaces their direct sum is the whole space and that they are all mutually orthogonal to each other. The eigenspace of lambda 1 is orthogonal to the eigenspace of any other lambda I, okay. So, this is just proof of self adjointness, and if you see essentially it is just this very simple lemma, that is all, just keeps getting used again and again. Okay, any questions on this? So, let us prove this in its most generality. So, this is the diagonalization theorem, this is sometimes called the spectral theorem for self adjoint operators. It says that any self adjoint operator can be diagonalized via an orthonormal basis. So, but then there is this general statement which operators can be diagonalized via an orthonormal basis, right. So, there is a more general class of operators which admit diagonalization, and these are called the normal operators. So, let us define that. So, again T from V to V is let me just say diagonalizable via an orthonormal basis. In other words, it has got an orthonormal basis of eigenvectors if and only if T and T star commute with each other. Okay, so, this is sort of the final definitive theorem, this is the spectral theorem for normal operators, this is a full fledged spectral theorem. It tells you which sorts of operators can be diagonalized. It says an operator can be diagonalized via an orthonormal basis if and only if the T and the T star commute with each other. Okay, observe the previous case when it is self adjoint, T is equal to T star. So, of course, they commute, that is, so it is a special case of this finally, but this is the most general version. So, let us prove this, let us prove one direction, let us try to understand how this condition even comes about, right. Suppose it is diagonalizable, why does that force T and T star to commute, okay. So, let us do that. Okay. So, suppose there exists an orthonormal basis of eigenvectors if, so what am I going to assume, if Vi 1 to n is an orthonormal basis of eigenvectors of T, in other words T Vi is some lambda I Vi. Okay. Then I claim that in fact these are all also eigenvectors of T star, the same vectors are eigenvectors of T star and the eigenvalues are just lambda I bar. Okay, you have probably seen this statement in the matrix setting where you actually try and prove it using matrices. but it has got a very transparent proof when we think in terms of this adjoints of operators and so on. Okay, so let us prove this. The claim is that T star of Vi had better be lambda I bar Vi. Okay. So, we will just write down that inner product equation that T star has to satisfy. So, what property does it satisfy? So, Tx comma y, so but I will apply it to Vi Vj is Vi comma T star Vj. I know that this is true for all Ij. Okay. So, now let us just unravel what both sides are. T Vi lambda I mean I do not know the right hand side, I know the left hand side. T Vi Vj is just lambda I Vi Vj because it is an eigenvector, and inner product of Vi with Vj is what? 0 or 1 because I picked an orthonormal basis. So, it is just lambda I times delta Ij. Okay. Now, what does this tell us about the right hand side? It says that if you look at this unknown vector that we are trying to find, this fellow T star Vj, we do not know what it is, but it is some vector whose inner product with each Vi I know. What is its inner product with Vi? It is 0 if I is not equal to j, and it is lambda I if I is equal to j, right. Is that all right? Its inner product of course in the second component rather than the first component. So, let me bring it to the first component if you wish. From here I conclude that T star Vj has the following property: its inner product with Vi is lambda I bar delta Ij. Okay, this is for all Ij. So, let me fix j and vary I if you wish. So, let us fix j written like this, but lambda I bar delta Ij means what? It is 1 only when I is equal to j. So, I will just change it to lambda j bar delta Ij, right. That change I can make because anyway it is 0 if I is not equal to j. Fix j? No, I do not need to fix j here. I can take j to be.
Can you explain that?
Why I am fixing j? You mean? No, or how I got this? Is it
Yes, that's
this step is okay? I just did bar of this. I just swapped the two sides. I should get conjugate if I swap it, right? See, these two are equal. Now I interchange, so I get T star Vj Vi, but then this fellow will become its bar.
So my left hand side is bar will be there.
Where?
T star of Vj comma Vi, the inner product, there bar will be there.
Correct. So I took bar on the other side also. See, but there won't be any bar here if you want, if you say that, right? Am I understanding you correctly? Yes, I can.
No,
Let's
sir.
do that.
Problem is Vi, you are changing, sir. That time you want to make one bar is required.
If I put equal to, okay, sure, I'll do that. Yeah, let me do it like that. So I didn't put equal there. I just meant implied, but let's put equal. So if you want to say this is equal to that, then I should put a bar. Yes,
Yes, sir.
correct. But then I should remove the bar from the other side. Let me remove fixed j also. Is it okay now?
Yes.
For all I. So Vi T star Vj is T star Vj Vi bar, but that is equal to lambda I delta Ij, right? And lambda I delta Ij is the same as lambda j delta Ij if you wish. Is that okay? Lambda I delta Ij is equal to lambda j delta Ij, because when is that non-zero? Only when I equal to j, right? So that is the only case I care about, otherwise it is 0 anyway. So whichever I write, the value will be 0 if I is not j, and if I is equal to j, they are both giving me the same answer. I should remove the bar from this also. Okay, so now we are done, because this guy here, this equation here is telling me what T star Vj Vi is. Let me take bar on both sides of this equation. So if I now take bar on both sides of that equation, it tells me T star Vj is that vector whose inner product with every Vi is given by this formula. This is true for all I and j if you wish. So for all I, let me think of j as fixed. So what does that mean? That tells me what T star Vj has to be, right? What is that vector which is firstly this is a vector which is perpendicular to all the vi's except vj itself, it is perpendicular to every other vi. So, in particular it means it has to be vj or some multiple of vj only. What multiple of vj is it? Well, it has to be this multiple, that is the only way. So, T star vj is equal to or if you wish, let us just write it out. See, we know its coordinates. See, we know the expansion of when I have an orthonormal basis, any vector can be written in terms of the orthonormal basis like this. No, these are the coordinates, but I know the coordinates. It is only one coordinate is non-zero, which is lambda j bar for vj. Is all right. Okay. So, what this means is my claim is true that if I start with an orthonormal basis eigenbasis of t, that basis is also an eigenbasis of t star, okay, with different eigenvalues, that is all, with lambda I bars. Now, why does that tell you that they both commute? Well, you just apply t followed by t star. So, just apply t star or t star t. What it will do is, because it is a simultaneous eigenbasis, it will just give you mod lambda square v, that is all. So, therefore, now let us prove commuting. If you apply t star t on any vi, it will just be lambda I bar lambda I vi. If you do t star also, it is the same answer, it is basically mod lambda square, both of them give you the same answer, okay, and this is true for all basis elements vi, therefore it is true for all vectors. Therefore, they commute, okay. So, this is one direction, that if t is diagonalizable via an orthonormal basis, then t star actually has the same basis and they both commute. Okay, let us prove the converse. Suppose t and t star commute, okay, then we need to show that t is diagonalizable, that there is an orthonormal basis. Okay, now this is an important property of commuting operators. See, suppose I have two operators a and b which commute, suppose. So, in general, no inner product, nothing. Okay. So, suppose I have two commuting operators, and if I take an eigenspace of one of them, okay, and let us say V lambda is the lambda eigenspace of A. Okay, lambda is some complex number. Okay, let us pick some eigenvalue. So, if I have an eigenspace of A, then B leaves that space invariant. This is a property of commuting operators. See, what one might actually like to have, but it is not true, is the following: if A and B commute, and if W is an invariant subspace under A, okay, if W is A invariant, then it is also B invariant. Okay, this is a bit too much to expect, so one can try and find some counter examples, but eigenspaces are somehow special. If I have an eigenspace, then it is a special kind of invariant subspace. Okay, it has got slightly more properties. Then eigenspaces will however be left invariant under B. Okay. So, let us prove this. So, proof is simple, I am sure you have seen this before. So, here is lemma. So, I need to show that if I take a eigenvector and I apply B to it, the answer is again an eigenvector for the same eigenvalue, right. So, how do we check that? We act A on it and see whether you get lambda times BV, right, A of BV, but now we use commuting, it's BAV, that is right. So, I have used the commuting property here, and lambda BV, which is exactly what I needed to prove. Okay. So, we have shown that if I take an eigenvector of eigenvalue lambda, then B acting on it is also an eigenvector of eigenvalue, and that is exactly what I claim. Sorry, what? BV, but 0 is in V lambda, no? Eigenvector, oh no, not eigenspace, it belongs to the eigenspace, yes, yeah. So eigenvector is always a non-zero vector, right? But so what I mean is it belongs to the same eigenspace V lambda. See, the eigenspace will have the vector 0 also, it is a subspace. Is it okay? Okay, now that is all we need, because now if you go back and remember how we did the proof of for self-adjoint operators. Okay, now let us just see how this proof can be modified. Okay, I do not need to write anything really, because this proof was sort of manufactured in such a way that it will actually work in the other case also. Okay, so instead of self-adjoint operators, I am going to take a operator in which T and T star commute, that is all I am going to take. Okay, now let us just copy the same steps of the proof. What are the first step? You take an eigenvalue of T and you write out that eigenspace, right. So, what we said in this case was T preserves that eigenspace, so T star preserves its perp, right. So, but T star was equal to T, therefore, we were done, right, and then that allowed us to sort of continue the process. Now, let us start the same way. Let me write out. So, I am now trying to prove the converse statement, this one here. So, I am going to prove the reverse statement. If T star and T commute, then I am going to show that T has a basis of eigenvectors. So, I know T star T, so it is the converse of my theorem. So, let us do the same thing. Let us take an eigenspace. So, let V lambda, so let lambda 1 be an eigenvalue and take V lambda 1 is the lambda 1 eigenspace of T. Okay. Now, suppose we use this lemma, then what does it tell us? I know that I have a commuting operator. T star leaves that subspace invariant, right. T star of V lambda 1 is subset of V lambda 1. T star leaves that space invariant, and now we are in business, because what does that tell us? T leaves, if T star leaves a space invariant, T leaves its perp invariant. Right, is okay, is all right. That is, it just seems like we did something fishy there, but essentially we just use the fact that V lambda 1, because of the commuting property, V lambda 1 is T star invariant, so its perp is T invariant, and now it is the same proof as before, right. This is exactly what was required. So, now we managed to say that V lambda 1 eigenspace of T, uska perp is again invariant under T. Now, again you look at T, same funda, T restricted to that subspace, again T star and T will commute with each other, because T star on that restriction is nothing but the restriction of the original T star to this, and you continue the same process. Okay. So, I am going to leave you to sort of complete the proof on your own. The basic idea in both proofs is really the same. Somehow you must start with an eigenspace, and in the first case, to show that its perp is T invariant, we simply have to use the lemma, that is all, because eigenspace is T invariant, perp is T star invariant, but T star equals T. In the second case, we need a different argument which will get to the same point. We just use this lemma about commuting operators and then get the same. Okay. Okay, good. So, this is the general spectral theorem. This is maybe one of the high points of linear algebra, at least related to orthogonality and so on. Now, what I want to do next is focus back on the self-adjoint case. Okay. So, let us go back to the self-adjoint operator. So, self-adjoint operator is it is a little bit more than, we can say a little bit more. We know it is diagonalizable, of course, that we also know for normal operators, but in what way are self adjoint operators more special than normal operators? T star equals T. So, the first observation is that its eigenvalues are all real. Maybe I should even formulate it as a proper theorem. Let T be a normal operator. So, let me start with the normal operator. So, in what way are self adjoint operators special in the class of normal operators? So, let T and T star commute. So, this is what we mean by T is normal. Then T is self adjoint if and only if all its eigenvalues are real. Okay. So, this is how self adjoint operators are special in the class of all normal operators. They are normal operators with the additional property that eigenvalues are real. Okay. So, I claim the proof was actually on one of the earlier slides along the way when we proved. So, this slide should tell us that this is true. Can anyone see the proof at this point? Okay, right. See, for a general normal operator we managed to prove this. For any normal operator this property is true. Firstly, it is diagonalizable, and if T vi is lambda I vi, those are the eigenvalue eigenvector pairs, then T star has this other property, that is lambda I bar vi, right. Now, when is T equal to T star? Exactly when lambda I bar vi is equal to lambda I vi, which means lambda I is equal to lambda I bar, and converse is also true. If lambda is equal to lambda I bar for all I, then of course T is equal to T star. They have the same action on the vectors vi. Okay. So, it is just this little box here, so that is the proof. So, I should say.
So, the hypothesis T and T star is commute is required.
Because that is the hypothesis of normalcy. So, if T and T star commute, that is when we were able to do this. That we will be able to get an orthonormal basis of eigenvectors of T, right, because we have proved this theorem. See, so how am I using the hypothesis? T and T star commute, therefore, by the previous theorem I know that T has an orthonormal basis of eigenvectors. So, I am using the proof of the theorem now, the spectral theorem.
Suppose I want to prove that the all eigenvalues are real, means it is not required that T is commuted, not required, because T and T star is T equal to T star is fine.
Say that again. What are your assumptions on T?
Suppose T equal to T star, the self adjoint operator, this directly implies eigenvalues are real. At the time we don't require T is obvious.
That is because T and T star, of course T is equal to T star, then they commute, correct. Yeah. No, I just want to sort of, yeah, I guess you could argue in various ways. So, the most economical argument is, we just reuse what we have done during the proof of the spectral theorem. So, what I have really said here, I mean, to complete the chain of arguments, T and T star commute. So, that is what we have assumed. So, normal operator, that means by the spectral theorem for normal operators there exists an orthonormal basis of eigenvectors. Let me call those eigenvectors as vi and the eigenvalues as lambda I. Then by what we already did before, and that does not require that T and T star commute. If I have an orthonormal base of eigenvectors, then I was always able to prove that T star must do this, right, by using just the definition of star. And now we just complete the proof. From here we conclude that if lambda is equal to lambda I bar, then of course it means T is equal to T star, and conversely if T is equal to T star, lambda I had better equal lambda I bar. Okay. So, this is the special property of self adjoint operators, and as soon as we have real numbers as our eigenvalues, what we will do is we will just arrange them in order. Okay, now it is on the real line. So, I can sort of say which is the largest eigenvalue, the next largest eigenvalue and so on, and this point of view, this analysis will in general turn out to be very important. Okay. So, let me say this. So, if T is self adjoint, we will arrange the eigenvalues. So, let lambda 1, lambda 2, lambda n, they are all real numbers, be its eigenvalues. Okay, maybe we should say let T equal to T star and let lambda 1, lambda 2, lambda n denote its eigenvalues. Okay. Now, here is the important property that these eigenvalues, see how does one typically determine eigenvalues? So, let us ask ourselves that question, how does one compute eigenvalues? We have sort of the algebraic method, which is that we write the matrix of T that form this polynomial out of it, which is T minus the characteristic polynomial determinant of T minus xi, and then try to solve for roots, right. So, this is the process that we use to find these numbers. Now, when the operator is self adjoint, it turns out we have a completely different way of finding the eigenvalues, okay, which does not involve the characteristic polynomial at all, but rather it sort of involves the geometry of the operator, meaning it sort of keeps it uses just the actions of the operators on vectors of norm 1. So, let me say it. So, this is a very important point of view again. So, let us determine. So, that is my notation. T is so lambda 1, lambda 2, lambda n are my eigenvalues of T arranged in weakly decreasing order. And maybe let us also write down the corresponding eigenvectors. Suppose V1, V2, Vn be the corresponding eigenvectors. Now, here is the observation, if I take T Vi, so T Vi is lambda I Vi, okay, now what I am going to do is I am also going to normalize them, be the corresponding eigenvectors, and I will ensure that they are orthonormal. So, let me take the orthonormal basis. So, you can always choose an orthonormal basis of eigenvectors, and what I will now do is compute. So, this is true for all I. If you now look at T Vi Vi, okay, the inner product of Vi with T Vi, then of course, the answer is just lambda I Vi Vi, but Vi Vi because of normalization is just lambda I. Okay. So, this is for all I. Now, of all the Vi's, which is the guy which will maximize T Vi Vi? So, what is the maximum value of T Vi Vi, okay, when I goes from 1 to n? Lambda 1, right. It is just going to be the first guy, because by definition that is my largest eigenvalue, right. Now, here is the beautiful statement. Here I have just maximized it on this particular eigenbasis, right. I have only looked at, these are just n numbers V1, V2, Vn, for each of them I have computed this quantity. So, it is lambda 1, lambda 2, lambda n. But in fact, what we can do is the following, consider, so let me call this S n minus 1. So, this is the unit sphere in Rn if you wish, but I mean I am working in general in a vector space. So, let me call this, just call it something else, the unit sphere in V, for example, just put some script S of V. So, this, what is this? Is the unit sphere, by which I mean you take all vectors in V whose norm is 1. Okay, in other words, they, or norm square is 1 or inner product is 1 if you wish. I mean the same as things whose norm square is 1 or inner product, let us not do that, whose norm is 1, that is easiest to think of. So what is this? If you think of Rn or Cn as your vector space, what I am really saying is that you take that space and you look at the sphere in it, right, just the surface of the sphere, everything only of whose norm is 1. Okay. Now here is the theorem statement. If you take vectors coming from this unit sphere and you compute this quantity Tv comma V, okay. So I am going to take this Tv comma V and I am going to take the supremum of this function as V varies over the unit sphere, okay. So supremum of course is like saying the maximum, but except if it does not exist, you still kind of approach the maximum, but I claim that, so what I am really doing is the following: on this unit sphere I am defining a function, okay, it is a function to, let us imagine my field is R for now. So for every point V on the unit sphere I am mapping it to the number Tv comma V, it is some real number, okay. So the first thing, that is something to prove, Tv comma V is a real number, so we will prove it along the way, but that real number so it is a function now, it is a real valued function on the unit sphere. The unit sphere is a compact set, right, okay. So let us recall a little bit of topology here. The unit sphere is a compact set in Rn and here is a continuous function on it. So this function TVV will also turn out to be continuous, it's because TV in some sense is just a linear function and you are taking inner product. So you can actually write a formula for it, it will be a very simple quadratic polynomial in the exercise. So here is a continuous function on a compact set. Now what do we know about such functions? They always, supremum is attained, right, there is a point at which this supremum value is always attained. So I can actually replace the supremum by the word maximum, right, because the supremum is actually attained somewhere. So it is a maximum on the unit sphere of Tv comma V. I claim that that is exactly this largest eigenvalue lambda 1. So the first equality that I have written is just this compactness argument, that supremum is actually attained, so I can replace the word supremum by the word maximum if I want. But the content of the theorem is really the second equality, that this maximum value is actually equal to lambda 1. Is fine, is the statement clear? It is a very strange statement, it sort of seems to come out of nowhere if you have not really seen this kind of stuff before, because we are always used to thinking of eigenvalues as the solution of the characteristic polynomial, right? It is an algebra problem finding the, but what we have done here is to reduce it to some sort of a geometry or a topology problem. Here is a function on the unit sphere, its maximum value is the eigenvalue, okay. But we sort of already see some hints of this, so let us prove this. The proof is very simple. So I need my vector V to vary over the unit sphere, right. So unit sphere means what? V can be written as Ci Vi. What is norm of V or norm V square? Let us compute norm of V square. Because the Vi's are an orthonormal basis, the square norm of V is nothing but summation Ci square or mod Ci square if you are over the complex numbers, okay. So what I know is that I am essentially allowing my vector V to vary over, the vector V is really the coordinate C1, C2, Cn, the summation mod square of the Ci's is 1, right, I am only allowing such Ci's, okay. Having done that, let us compute what this function value is. So what is Tv comma V? So firstly let us check that TVV is by the way always a real number. See, Tv comma V is actually a property of star, it goes to the other side, right. So TVV is actually V comma TV, V comma T star V, but then T is self adjoint, so T star is actually T. So now what have I proved? I have shown that TV comma V is equal to its bar, right, because V went to the other, T went to the other side, so it is just the bar now. So what does that mean? It tells me that TV comma V is equal to its conjugate, therefore it is a real number. Okay, so that is a fact that I mentioned, that TVV, this function is actually a real valued function. Continuity I will leave, it is easy to check. Now, so let us actually compute TVV for that this particular vector that we wrote out. So, the vector V was summation Ci Vi. So, when I apply TV, it will just give me summation Ci lambda I Vi, and when I take inner product of the two TV comma V, Vi's are an orthonormal basis. So, I will only get the Ci lambda I and Ci bar. I just need to multiply out the constants together, that is all, the coefficients together, right. But that is just summation mod Ci square lambda I. So, if I compute TVV, it is this quantity, right. Now, can you see why this is at most lambda 1? What is an orthonormal vector? No, I am just saying this quantity, this real number, summation mod Ci squared lambda I, the maximum value, I mean it is bounded above by lambda 1.
These Ci's are less than 1.
Okay. Ci's had a property, right? What is the Ci property? Summation Ci square is equal to 1. So, now it's we just have to correctly set up the inequality. Right. So, you just have to replace all lambda I by the corresponding lambda 1, that is all. See, lambda I is all the, I mean lambda 1 is the largest eigenvalue, right. So, every lambda I is less than or equal to lambda 1. So, mod Ci square lambda I will multiply both sides of this inequality by mod Ci square, and now I will sum both sides, right. But now lambda 1 will come out of the summation, it is lambda 1 summation Ci square, that is 1. So, we are done, right. So, this particular quantity on the left is at most lambda 1, and but it can attain the value lambda 1. When can it be equal lambda 1? C1 alone is 1 and all the other Ci's are 0, right. It is for the eigenvector itself. I can take my vector V to be just the first eigenvector. So, observe that T V1 is, as we computed already, this fellow is exactly lambda 1. This corresponds to taking first C1 alone to be 1, other fellows to be 0. Okay. So, therefore, we have proved our statement. So, that is the thing that we needed to prove. The supremum, so it's firstly it is bounded above by lambda 1, but the value lambda 1 is actually attained, therefore, lambda 1 is the maximum, fine. Okay. So, likewise we have a bunch of other statements. So, similarly how will we find what is lambda n? We can give a geometrical interpretation like this of lambda n as well. What should we do?
Nth largest eigenvalue.
Nth largest eigen, but how will you get that from this geometrically? Square free, sorry.
Coercitivity, we can use the whenever the curve will be, the matrix will be the my graph will be, that's a conflict, like the coercitivity, very where is the minimum will occur at the time coercitivity will consider.
No, but how will you, I mean, so what is, I just want a candidate for, I don't know, function or maximum or minimum or some such.
Sir, local minimum will occur because of that lambda 1 will come. So, coercitive means minimum, the various problems we are considered means the curve is coercive means some eigenvalues, the smallest eigenvalue only we are considered.
Correct. So, that is what you want to do, you want to take the minimum, the smallest eigenvalue. So, I mean the thing to do is just replace max by min. See, if I just did that simply, I change maximum to minimum, then it works, right? Then what I will get is exactly my, so let us modify the theorem again, theorem part 2 if you wish, just says if I take minimum of the same function TVV, V ranging over the unit sphere of V, then that is just going to be my smallest eigenvalue. Okay, proof, exact same proof, we just have to replace instead of what we did at the very end, right. Sorry, where did we do this? Oops. So we did this here. So I said summation C A square lambda is less than or equal to lambda 1, same also tells me it is greater than or equal to lambda n, right. So the same logic will tell me it is greater than, it is bounded below by lambda n, and lambda n is of course attained at that particular point when you take the last eigenvector. Okay. So if you replace max by min, then what you end up getting is exactly the other statement. Okay. So these are these two guys. Now the interesting thing and important thing for many applications is how do you get the other fellows. Okay. So that's something that actually arises in applications. Okay. So the question now is the following: lambda 1 and n I know how to get. How will I get the second eigenvalue?
I will take the perpendicular of the first eigenspace. Try to find the eigenvalue row there.
Right. So you first find the first eigenspace. The trouble is that this process only gives me the eigenvalue, right? See, if I take the supremum of this function, I mean you will, of course you will have to maybe look at the point at which it is attained. The thing is, yeah, you are right, you could do that, I suppose, if you can somehow find the point. Yeah, okay, but the thing we want is a characterization like this in terms of maxima and minima and so on. Okay, can we somehow realize the second eigenvalue as some kind of maximum or minimum or some combination? Okay, so let us answer that question. So to answer it, let me first give you just a baby version of this or a completely different context. Let us do it in case of n numbers. Okay. So I have got let us say I have a list of n numbers, n real numbers maybe. Okay, we call them a1, a2, a3 and so on. So I have 7 numbers here, distinct real numbers. Okay. A1 of course is just obtained by saying take the maximum of these numbers. A7 is just the minimum of these numbers. What we are trying to ask is what is A2, right? Something like that is what we are asking. So here is the solution. Instead of taking just that one, taking how do you find maximum? You put your hand inside the bag, you pull out one number, you put your hand in again, pull out another number, see if that is larger, pull out another number, see if which is larger so far and so on. So imagine picking numbers one by one from a bag, and then out of all the numbers that you have gotten, you find whoever is the largest. That guy is A1. Okay. Now what you do is you put your hand inside the bag, but you pull out 2 numbers at a time. Okay, don't pull out one number, pull out 2 numbers. Okay, so maybe I put my hand in and I got these 2 guys. Okay, of these 2, I only note down which is the minimum. Okay, so pull out 2 numbers, only remember who is the minimum of the 2. Okay, so if I pulled out A3 and A6, I will remember A3 the first time around. Now again I put my hand in, I pull out 2 numbers, I see who is the minimum. Okay, so maybe I pulled out A3 and A5 the next time, then I remembered A5. Okay, do it again, maybe I pulled out A4 and A7, okay, A7 is the smallest fellow. Okay, and so on. Okay,
I will take the maximum of the minimum.
okay. So which is the one number which will never appear when you do this? A1 will never appear, right? Why? Because I am taking the minimum. I am pulling 2 fellows out, no doubt, but I am always taking the minimum of the 2 guys. So even if A1 and A2 were chosen, for example, as the 2 numbers, the minimum guy of those 2 is A2. So A1 is never going to appear in my list. Okay. So in a sense, this is how A1 got excluded from, like you were saying. So I want somehow to exclude the maximum guy and pick the next fellow. That's the idea. But the way you do it is you take 2 by 2 and then take the minimum, so that A1 will never occur. But then from this list, how do I find which is, what is A2? How do I get A2 from this list? It is the maximum of all these possibilities, right? When will it occur? How will A2 occur here? If A2 occurs here, which two numbers would I have picked? A1 and A2. In fact, there is only one possibility. I could have only picked, I put my hand in, and if I got A1 and A2, only then will A2 be the minimum guy. For every other possibility, the minimum is strictly smaller than A2, right, some other number. Okay. So, this is a minimax approach. So, what this is saying is A2 is the following, it is the minimum of k, where what is k? So, it is the maximum of this number, minimum min k just means the minimum number of the set k, where k varies over all subsets of cardinality 2. Okay. So, this is max over min. So, this is max min if you wish. So, this is max. So, I mean we do not often write it in the set notation. So, max k subset of this ambient set, let us give this set some name, L. Okay, this is A2. Okay. Now, let me ask you a question. Now that you sort of know the idea, can you also get it as min max? No, I want A2 again. I want to realize A2 itself as min of max. Huh? I claim it is min max k, where k varies over subsets. You have to complete the sentence. Cardinality 6. See, there is a certain complementarity to this. If instead of taking subsets of cardinality 2, if I pick subsets whose complement, sort of the complementary cardinality, so 2 I take 6. Okay, it has to be 6, not 5. So, I should choose number of elements plus 1 minus this cardinality. So, let us see why it will work. So, if I take 6 elements, right, then what are all the possibilities? Out of these 7 I pick 6, and then I take the maximum of these guys, right. What will the maximum usually be? Suppose I pick the numbers A1 through A6, maximum is A1, right. If I picked A1, A2, A3, A5, A6, A7, still maximum is A1, right, and so on. So, most of the time I will get maximum as A1 only, but there is one case when I will get maximum as A2, right, which is when I pick A2, A3, A4, A5, A6, A7, these 6 elements. For those 6 elements, the maximum will be A2, right. So, I take, when I say max over all possibilities whose cardinality is 6, this list if you see it will be almost always A1, but once it is A2, right. And so, to pick out that A2, all I have to do is just say take the minimum of all these maxima, that minimum is exactly A2, right. And now we are ready to just generalize it to anything. If I want to say I want to pick AI, there are two ways of doing it. I either take max min k, where k varies over subsets of cardinality I, or min max k, k varies over subsets of cardinality n plus 1 minus I, okay, n being this number 7 in this case, n is the cardinality of it. So, that is the complementary number that I need, right. 8 minus 2 is what I needed in that case. Okay. So, this is fine. So, there is this minimax way of trying to get any given number. Now, of course, the point is all of this has to be done for operators. Okay. So, remember how we converted this to, see, we said we will now take max of TVV over V ranging out the unit sphere. That is, I mean, this discrete case that I just told you is as if you are working only with these n numbers, TV1, V1, TV2, V2, Tvn, Vn. Out of those n numbers, if you had to find the maximum, to find lambda 1, you would just take maximum. If you wanted to find the second number, you could do what we just said and so on. But now we are trying to do this in a geometrical fashion, right. We do not know what the eigenvalues are, we do not know what the eigenvectors are, but all we have in our hands is the unit sphere, and we have the operator, and we have the inner product. You can play with them. So, let us do the same thing. So, this is the important theorem in this business. It says theorem. So, again T is self adjoint, lambda 1 through lambda n eigenvalues. Yes, let's do it for lambda 2 first, maybe. We should do it for lambda k. Let's do it for lambda k. So, the kth eigenvalue is the following. It is, let's do max min first. It's max min same function, the function is the same. TVV is all the time, that's a guy you are trying to maximize or minimize or min maximize, whatever. So, TVV, now what does V range over? V ranges over the unit sphere intersect a subspace W. Okay. So, it is a sort of a section of the unit sphere where what is W? W runs over all subspaces of V of dimension k. Okay. So, notice this is a bit like see earlier the cardinality k now gets replaced by dimension k. Okay. So, so this for all k, and then there is a max min likewise, or rather min max, you can say it is minimum of maximum TVV, V running over the unit sphere intersect a subspace W, but W is of complementary dimension. Complementary in this case being n plus 1 minus k. Usually complementary will mean n minus k. In this case we need dimension n plus 1 minus k. Okay. So, this is sometimes called the Courant-Fisher minimax minimax characterization of the eigenvalues and so on. The beauty is that it's a purely geometrical kind of thing, right? Some action taking place on the unit sphere and on various sections of the unit sphere. That's the nice thing. So, before we prove it, the proof itself is not too hard. Let's just look at lambda 2 for example. So, what would lambda 2 mean if you are in a 3-dimensional space? Just get some intuition for what this looks like. Example, if V is say 3-dimensional, and that middle guy is what I am trying to figure out. So, what would we do? So, inside this 3-dimensional space, I have got the unit sphere, and this lambda 2 it says is you take max min. So, in this case min max and max min are both dimension 2, right, because 3 plus 1 minus 2 is also 2, you can write it either way. Therefore, max min of TVV, V in the unit sphere, V is also in W and W is of dimension 2. Okay. So, what does this mean? This just says the following: I need V to run on the unit sphere, but it should also lie on a subspace W. In other words, I cut the sphere by plane. Plane is a subspace of dimension 2. So, what will I get? I will get a unit circle, right? I will get a circle on the sphere. So, it is a section. So, what I am now doing is saying the following. See, lambda 1 itself is obtained as follows, right? Lambda 1 or lambda 3. See, what is lambda 3? It is just minimum of this number over the whole sphere, the smallest eigenvalue, right? So, I am just finding minimum on the whole sphere. That is like saying, let me do it in 2 steps. I will first find the minimum on this section, on a on this circle. So, first find the minimum on the circle, and then further minimize over all circles. Right? This is a silly way of saying it maybe, but I am just writing like this to contrast it with lambda 2. See, what is lambda 3? The minimum eigenvalue, I can do it in 2 steps also. I can say first let me cut it by a plane, I will get a circle, I will find the minimum value of the function on the circle. Then I will vary the circle, let me take all possible 2-dimensional things. So, it is like I will just, I have many circles on this sphere. On each of these circles I find out what the minimum is, and then I take the minimum for all those minima. That is the global minimum, right? That follows lambda 3. Now what we are doing here is this interesting process. Again, two-step process. First cut by various planes, you keep getting minima, but I take maximum of all those minima. Okay, and doing that gives me lambda 2. It's absolutely somehow mind-boggling. I mean, something like this turning out to be true is, it's always a very surprising sort of statement. Okay, so that is lambda 2, and I mean you can also do a max-min version of this. You know, you can also write it as min over max of all such circles. So it's basically this process. You first cut by some k dimensional space, you get some section of the sphere, not the whole sphere. You minimize on that section, and then you maximize over all possible sections. Okay, that guy will give you the kth eigenvalue. Okay. Let me just take a decision on whether I should prove this right away. So maybe let's do it for lambda 2. Okay. I just do it in general. Let's just do it in general. Let's do it for the kth guy. So the proof is more or less exactly what I gave earlier. So let's prove this. So what should we do? We take V to be some V should be an element on the okay, sorry, how should we prove this? So we should take a subspace of dimension k. So if I take my eigen basis as before, so let's take V1, V2, Vn, Tvi is lambda Vi, and we will write V as a linear combination. Yeah, correct. No, let's not write V as a linear combination. So okay, now what are we trying to do here? We are saying let's fix a subspace of dimension k. Okay, fix W whose dimension is k, and I am going to take that section of the sphere. So I have the unit sphere, and I mean here I am drawing it like a circle, but this is like W intersect the unit sphere. So observe, W has dimension k, right? So what does it mean? That means W will necessarily intersect the following set. So I claim that the following is true, that W will have to intersect, I am doing minimum or maximum. So max. So W, look at the first n plus 1 minus k vectors. So consider the following. Okay, so it's slightly trickier than the earlier proof, but here's the idea. So we have to somehow do this max min. Okay, to do that we should let W vary over all k dimensional subspaces. Now what is one obvious k dimensional subspace? Okay, which is W1, W2, Wk itself. Sorry, V1, V2, Vk, the first k guys. Do I want this or the other k? No, I think I want this. So let's try this. So W, now consider the following. Look at the space W and look at this space which is of dimension. So what is the dimension of this space? N plus 1 minus k. This fellow has dimension k, right? So the sum of the two dimensions is n plus 1. It is more than the ambient dimension, which means that these two fellows have to necessarily intersect. Correct? Is it right? How would you prove that, for example? So there's this dimension formula, right? If I have a dimension of a sum of two subspaces, dimension of, subspace W1 plus W2 is dimension W1 plus dimension minus the intersection. So since dimension of W1 plus W2 can be at most n, there has to be some intersection for that identity to be true. So this intersection cannot be 0, it has to at least have some vector, right? Can't be 0. So, there is some vector in this space which is in W. So, that is the point, that is what I really want in this case, I suppose. So, there exists a vector V in W such that V is a linear combination of the first n plus 1 minus k vectors, n plus 1 minus k of the Vi's. Now, for this V, what do I know about TV comma V? I know that TV comma V is what, less than or equal to, it's less than or equal to, I'm going to tie myself up in knots here. So, so I know two things about such TVV. On the one hand, it's less than or equal to lambda 1. On the other hand, it's greater than or equal to lambda n plus 1 minus k. Right? Because those are the two extremes of this. And now the minimum of TVV on this section is therefore probably want the other side. Okay, so I probably will have to think about this a little bit more. So, okay, let me get back to this tomorrow. So, let us postpone this for the moment. So, it is choosing the correct subspace. So, I am now wondering if I should choose this n plus 1 minus k or the other guy from the other end, choose W V n and so on, n plus 1 minus k fellows. That is probably what I should do. That is the other possibility. So, anyway, let me figure that out. So, you should choose Vk plus 1 till Vn. So, my guess is that this is probably the correct thing to choose. So, I am choosing the wrong guy. Okay, anyway, so let me get back to this tomorrow maybe. But let us analyze what this gets us. Okay, and this is a very important statement, and in fact, also from the point of view of applications. So, we'll also look at that soon. So, the point here is it allows us to conclude all sorts of things about eigenvalues which you wouldn't be able to conclude purely from the algebraic point of view. Okay, so that is the real usefulness of this. So, here's a corollary. Suppose I have two operators, suppose T1, T2 are both operators, let us call it maybe T and S or A and B maybe. So, suppose I have A and B from V to V both self adjoint, then this implies that A plus B is also self adjoint, okay, just by the property of star. It is A star plus B star, which is equal to A plus B. So, the sum of two self adjoint operators is self adjoint. Now, here is the corollary to this geometrical characterization of the eigenvalues. The top eigenvalue of A plus B is at most the sum of the top eigenvalues of A and B. Okay. So, the first eigenvalue, meaning the largest eigenvalue of A plus B, is less than or equal to lambda 1 of A plus lambda 1 of B. So, where when I write lambda 1 of something, I mean lambda 1 of an operator T just means the largest eigenvalue of T. So, why is this true? So, observe, this will be a royal pain to prove if you are trying to do it from the determinant, whatever characteristic polynomial point of view, because you will first have to write out characteristic polynomial of A plus B, somehow try to find out which is the maximum of those eigenvalues, and then try to prove an inequality like this, right. But from this geometrical perspective, it's just more or less obvious. Okay, so let's prove this. What is lambda 1, the largest eigenvalue? It is realized as the maximum of A plus B x or V comma V, where V ranges over the unit sphere. Okay, but A plus B V comma V, let us write that out, is AVV plus BVV, and observe each of them is less than or equal to the corresponding maxima, right. Some AVV, it is a particular number, it is less than or equal to AXX where x ranges over the unit sphere for sure. Likewise, BVV is some particular value of this function, so that is also less than or equal to Bxx as x ranges over the unit sphere, and that is your inequality. Right? This is fine. Likewise, the minimum of a plus b, the minimum eigenvalue of a plus b is greater than or equal to the sum of the two minimum eigenvalues, exactly by the same thing. Okay, and
my different side is if I take the maximum, why is that time inequality? Why the problem is equality instead of inequality?
sorry, say that again. Why is
Suppose if you are not taking the maximum of left hand side, only right hand side only you are taking the maximum. I agree, sir, but what I am saying is,
no? So see each value. So maybe the correct thing to say is that for every vector v, I have proved an inequality, right? I have proved that a plus b v v, fix any vector v in the unit sphere. For that vector v, so for all v in the unit sphere, a plus b v v is less than or equal to lambda 1 plus lambda 2, lambda 1 lambda 1 a plus lambda 1 b, sorry that was wrong. This is what we have proved, right?
the same way similarly if you are taking different side is a v comma v plus b v comma v if you are taking,
Where
then
left hand side meaning here,
so suppose in my right hand side a v comma v plus b v comma v if I take it, my right hand side I can write it as inner part of a comma a plus b v comma v I can write. Then I
yes,
will take the maximum I apply,
yeah.
that time lambda 1 of a plus b will come.
No, when you apply maximum, why is it true that your equation, no, I do not understand, where are you applying maximum? See, you are starting with this equation, right? You are starting with this equation. If you cannot simply put maximum on all three sides and it will still be equal.
No sir, I am arguing that if I take inner part of a v comma v plus b, inner part of b v comma v equal to inner part of a plus,
Yes, that is this equation, that is
yes, that is that twisted side.
correct. Now
Then
you are
I
saying
take
put,
apply right hand side only the maximum I apply now.
No, that value will be less than or equal
That's
to
why
the
this is
maximum value of that.
correct. See, for a given v, you are just saying put maximum on this side.
Yes.
Okay, if you put maximum, then why is it still equal?
No, I am saying that at time the inequality is greater than or equal to lambda 1 of a plus b will come, sir. Left hand side. So that is the same argument if you are applying there, then it become equal will come.
No, it's the other way around. It's this inequality. Lambda 1 of a plus b is greater than or equal to maximum. See, why will that become greater? The inequality is in the reverse direction.
It's okay, sir.
Right? The way you are saying it, you will not be able to conclude anything. Because for a given value is less than or equal to the maximum value. Right? The value at v is a particular value of that function. Particular value of the function is less than or equal to the maximum value of the function. Yeah. Okay. So but the point here is see, how are we concluding finally is because of the following. We are now saying you take a given value a plus b v v for a particular v. In fact, for any v is at most lambda 1 a plus lambda 1 b. And now I am saying, okay, now I take, because every value is bounded above by this, the maximum is also bounded above. So since this is true for all v, it is also true for the maximum. That is the argument we are giving. Okay, and that maximum is exactly lambda 1. Okay. So this is something about lambda 1, right? I just concluded this. Now there is another important fact which comes up from the point of view of applications. So all of this is leading up, so next time, to what is called the principal component analysis, which is used in I guess in data science, and also related to the singular value decomposition and so on. But all of this is finally some analysis of eigenvalues, the top eigenvalues, what are the inequalities satisfied by the eigenvalues, things like that, right. So, some geometrical understanding. So, all of this is sort of the theoretical underpinnings of many of these methods. Okay, so I want to talk about another inequality. So, this inequality I talked about is only telling you something about the largest eigenvalue of a plus b, for example. Okay. So, this next statement is not about a plus b, this is about restrictions. So, restrictions are things like this. See, suppose I take, let us say I have an operator, I have a self adjoint operator, let us say t equals t star, and let us say I have written its matrix with respect to some basis, right. I have some matrix. So, the matrix with respect to some orthonormal basis. So, that matrix will become some Hermitian matrix, meaning A will become equal to A star. Okay. Now, what we often want to do is to say, okay, I do not want the full matrix, I will only take some principal submatrix, by which I mean I will take the first r rows and r columns. Okay. So, I had this big n cross n matrix, I keep only the first r rows and r columns and forget about the rest, delete or put zeros in the rest. Okay. This is some kind of truncated matrix, I will call it A tilde. Okay. Now, if the original matrix was Hermitian or self adjoint, what about this cutout piece? Also Hermitian, right, because Hermitian just means what? If you do transpose conjugate, it should give you back the original matrix. This is only some principal submatrix, right. So, I do transpose conjugate, of course, it's a part of the original, that is all. So, cutting it out in this manner still produces something which is Hermitian, but of smaller size. The original guy is n cross n, this fellow is some r cross r, right. But I can still ask the same questions. What can I say about the eigenvalues of the eigenvalues are again real. Look at the r eigenvalues of this smaller submatrix. How are they related to the eigenvalues of the bigger guy? Okay. Lies between means what?
The consecutive two means if the A has eigenvalue lambda or lambda 2 lambda
Mm.
and B is the principal submatrix of A
Mm.
and the eigenvalues of B are mu1, mu2, mu n,
Mm.
then mu I lies between that time eigenvalue will be mu1 to mu n minus 1.
Okay, so you are taking the n minus 1 principal.
So the eigen mu I will be lies between lambda I plus 1 or lambda I minus 1.
Right, okay, fine. What is this theorem called?
Cosine.
Okay, so there is this important theorem, okay, which says the following. So, I mean here r cross r is much smaller than n cross n, but you can imagine doing it in many stages. So, first I will just imagine deleting this last row and last column alone, right. So, from n cross n I go one step lower, I go to n minus 1 cross n minus 1, right, and I get this truncated matrix. Okay, let us give it a name. This overall guy is called A, this truncated fellow is called B. So, B is n minus 1 cross n minus 1, it is also self adjoint. So, you can write out the eigenvalues of B. So, I will do two things, I will write out the eigenvalues of A, of B, sorry, as mu1, mu2, mu n minus 1. I will write the eigenvalues of A as lambda 1, lambda 2, lambda n. So, this bottom guy has n fellows, that next fellow only has n minus 1, and the statement is most easily remembered by means of this picture. So, if you just imagine that there are n guys, n eigenvalues on the bottom, the n minus 1 fellows, the eigenvalues of the previous are best thought of as sort of these dots. Okay. So, what are these? What do I mean by writing it like this? It just says that if this is lambda 1, lambda 2, lambda 3 and so on, then I have got these inequalities. So, remember lambda 1 is bigger than lambda 2, right, but when I kind of put this on top, what I mean is that this fellow lies between these two numbers, right. So, that the mu 1 I am thinking of as it's some number which lies between lambda 1 and lambda 2, the first two eigenvalues. So, here is the thing, lambda 1, lambda 2, mu 1 is between them. Okay, then I have lambda 3, mu 2 is between them. and so on. So, final guy is lambda n minus 1 lambda n and mu n minus 1 is between them. Okay, so, this theorem is called the Cauchy interlacing theorem. So, this sort of configuration is called interlacing. I have got n fellows and this fellows kind of go and sit in the middle. So, this is called interlacing. So, this is called the Cauchy interlacing theorem for eigenvalues. Okay. Now, this sort of happens successively, meaning I can now go all the way to r cross r, right. I delete one more row column, one more row column, one more row column and so on. In fact, I can go all the way to the top till I get a 1 cross 1. Okay. So, what am I generating? I have n eigenvalues for this fellow, n minus 1 in the previous, n minus 2 in the previous and so on until I finally get down to just a single eigenvalue. So, that configuration can be arranged in a similar form, this dot thing. So, for example, if this fellow has the ambient guy has size 4, then I delete 3 cross 3, I get mu 1, mu 2, mu 3 which lie between the lambdas. Then I go one more step, I get some guys which lie between the previous fellow, and then one more which lies between these. Okay. So, this actually gives you successive interlacing thing. This is sometimes called a Gelfand-Zetlin pattern. Or successive interlacing pattern if you wish. And the eigenvalues of a Hermitian matrix and all its truncations always have that property. Okay. Now, so this is of course something which you can prove purely from this minimax criterion. So, that is an interesting part of this. You can actually sit down, you know what is each of the eigenvalues, you can compute it, then you must do it for the truncation and so on. Okay, so, we will not get into this, but I just want to record one little corollary of this which is necessary for this whole principal component analysis business that we will talk about next time, which is, see, if I truncate it to anything smaller, any truncation. So, here is the operator point of view if you wish, without going into matrices. See, suppose I have a self adjoint operator on V. What does its truncation mean? So, truncation is the following, I take a subspace W of V. Okay. Now, the truncation of T to the subspace is defined as following. So, I do not know how to call it, T dagger, no, it is not used. What is reasonable notation? T W maybe, truncation of T to W is just the following operator. Okay. How do you truncate? What is the idea of truncation? Just the matrix idea again. You only want to keep this portion, this is like the W portion, then you want to make everybody else 0, right. So, first we will make the remaining vectors 0. How do we get rid of all these remaining basis vectors? We first project, let P be the projection, let P be the orthogonal projection to W. Okay. So, first what I do is, I have many vectors, I first apply my projection P. When I apply my projection P, what will get killed? W perp will get killed. Okay. So, imagine these are all basis vectors of W, those are the basis vectors of W perp. So, W perp is all killed because I first applied my projection. So, I have gotten these zeros. Okay. I am forming this truncated operator. Then what do I do? Okay. For the remaining guys, for elements of W, if I apply the projection, nothing happens, they remain as it is. On those guys, I will apply my original operator T. Okay. So, on these fellows, I try to apply my operator T, except when I apply it, I will get also some non-zero entries below here also. This portion also will give me something non-zero, right. When I apply T to a vector of W, I will get some answer in W and some answer in W perp, but I do not want the fellows in W perp. So, what do I do? Just apply P again. See, P is your way of killing everybody in W perp. If you want to kill somebody in W perp, you just apply P wherever you throw them out in this manner. So, this is what truncation is in general, okay, without any reference to matrices, vectors, bases, nothing. If you have a subspace, I can define a truncation to it. Just apply P, then T, then once more truncation, once more a P. Okay. And now it is easy to see that this is self adjoint, because what is the truncation ka star? It is just PTP ka star, but that is what P star, T star, P star. And what is the property of an orthogonal projection? It was self adjoint, that was an if and only if condition, right. So, this is P and T is assumed to be self adjoint and this is P again. So, general truncations are always self adjoint for this reason, it is just PTP. Okay. And now the theorem, maybe I will not prove it, but it just comes for example from Cauchy interlacing. It says that the truncation eigenvalues, if mu 1, mu 2, mu r are greater than equal to, sorry, I have to arrange them in decreasing order, eigenvalues of the truncation, then they are all bounded above by the corresponding eigenvalues of T. Okay, where lambda 1 okay. So, this is a statement about truncation. You can prove it in fact from that Cauchy interlacing, because if you see how that works, I have lambda 1, these are next 3 eigenvalues 2, 1 and so on. So, imagine I am doing a truncation to a 2-dimensional space, okay, and those are my 2 eigenvalues. Then what are my inequalities? This fellow is bigger than this fellow is bigger than this fellow. So, this is my lambda 1, that is my mu 1. So, this lambda 1 will be bigger than mu 1. Likewise, if this is lambda 2, that is more than this, that is more than this. So, lambda 2 will definitely beat this guy mu 2 and so on. So, interlacing just means that I have those inequalities, right. So, what this finally implies is that the first r eigenvalues of the truncation are bounded above by the first r eigenvalues of T. Okay. Okay. So, I will stop here, but this we will remember this theorem, keep this in the back of your mind for tomorrow, because this is going to be important for this whole business of principal component analysis. So, this is the whole crux of that principal component analysis, just keeping the top r eigenvalues and so on.